Hello everyone, welcome to our first online video lecture for Physics 102 this semester. I wish we could do this face-to-face in the most effective way, but under the circumstances with the coronavirus, we're going to do our best with the distant learning and online videos. Now in this video, what we are going to do is we are going to look into the determination of electric potential from electric field. And I know that many of you guys have already done this in class. But as it turns out, there are a couple sections which did not get a chance to go over this subject due to lack of time. So this is what we are going to do first. For those who did this before, I think it's still a good idea to go over this video because the method that we are going to be discussing here, we're going to make use of that quite a bit in the next chapter when we calculate the capacitance of capacitors with different geometries. So let's not waste any more time and get started. So this is the expression that we are going to make use of here, which is telling us that the potential difference between points B and A will be equal to the negative of the integral of E dot dl from A to B. Now we derive this expression by considering the change in electric potential energy and the work done by us, or the negative of the work done by the electric force. But I'm not going to go back into the derivation here. I would rather focus my attention on how to apply this expression to calculate or to find the electric potential at a given point. Now, what this expression is telling us, maybe I should summarize that for you. If you go from point A to point B, let's say, for the time being, let's imagine that you follow a path like this. We are going to have to divide this path into many dl vectors, which are infinite small displacement vectors. Imagine that this is one of them. And we are going to find the scalar product of the dl vector with the electric field within that dl, which is going to be, by the way, the change in the electric potential if you go through this tiny displacement vector, which is negative of A dot dl. So we're going to have to do that for all the dl vectors. We calculate the change in electric potential within each one and add them up, which is going to be the right hand side of this equation. Now before I go ahead and apply this to solving problems, I want to point out a couple of things that we can conclude from this expression. The first one is, if you move in the same direction as the electric field, meaning the dl vector and the electric field are in the same direction, the change in the electric potential will be negative because the scalar product will be positive, but since you have a negative sign here, you will have a negative change in electric potential, which means if you move in the direction of the electric field, you will see a decrease in electric potential. And if you move in the opposite direction to the electric field, then the scalar product will be negative. But since you have a minus sign here as well, the whole thing will be positive here. So the change in electric potential will be positive. Again, what it is saying to you is, if you move in the opposite direction to the electric field, you will see an increase in electric potential. The third possibility here is when you move perpendicular to the electric field. If you move perpendicular to the electric field, then the scalar product here will be basically zero. What it is telling you is, if you move perpendicular to the electric field, the electric potential will not change. One more thing that I want to mention here is related to the path that we chose here. Now, remember, this expression, we derived it considering the change in the electric potential energy. And the change in electric potential energy only depends on the initial and the final configuration of the system in question, which means this integral does not depend on path. You could as well move on a path like this and you will find the same electric potential difference. So it doesn't matter which path you follow. As long as your final point and initial point are the same, you are going to get the same potential difference. So whenever you face a problem, if the choice is up to us, I would choose the easiest path possible because, again, it doesn't depend on the path. Alright, now that we remembered the relationship between the electric field and the electric potential, now let's solve some examples, starting with a spherical conductor which is said to have a positive charge Q on it. We need to find the electric potential anywhere inside the sphere as well as outside the sphere. Again, we are going to make use of this expression here, which is VB minus VA is equal to minus from A to B E dot dl. Now, in order for me to be able to use this expression to calculate the electric potential inside and outside of this conductor, what I need to know is the electric field here. So how am I going to calculate this electric field? Now, if you guys remember our discussions on Gauss's law, you already know the answer to the electric fields that we need to use here. But what I'm going to do is I'm going to quickly calculate these electric fields for you in the next board. And then we will move on from there. Without going too much into detail, let's quickly find the electric field inside and outside of this conductor. So I will start with the electric field inside, where R is less than R0. Now, I think what we should do is we should draw our conductor here. Now, since we want to find the electric field inside, we are going to draw a spherical Gauss surface inside as well. Now, the Gauss's law states that the electric flux through a closed surface is equal to the enclosed charge divided by epsilon 0. Since this is a conductor, however, the charge will be on the outer surface of this conductor, the charge Q. And what this means is, within the Gauss surface that we just draw, the enclosed charge will be equal to 0, which means, since we have a spherical symmetry here, the electric field inside will be 0 as well. Now, what about the electric field outside, where R is larger than R0? Now, again, let's quickly draw our conductor here. Now, since we are interested in the electric field outside, I'm going to draw my Gauss surface outside as well, where R is larger than R0, obviously. Now, again, if you write the Gauss's law here, the net flux through our closed surface, Gauss surface, is going to be equal to Q enclosed over epsilon 0. Since the electric field will always be perpendicular to the Gauss surface that we choose, this integral will become E times dA. Okay, let's just quickly write it, E times dA. And since the whole conductor is within our Gauss surface, then the enclosed charge will be simply the total charge of the conductor. Now, since I expect the electric field to be constant in magnitude on the Gauss surface due to symmetry, I can take it out, and this is just going to give me the electric field. Now, you will have just dA left here, but you know that that's going to be the total area of the Gauss surface, which is 4 pi r squared for a sphere, is equal to Q over epsilon 0. If you solve this for the electric field, what you are going to get is 1 over 4 pi epsilon 0 Q over R squared. And if one needs to write this as a vector, we can write it as 1 over 4 pi epsilon 0 Q over R squared R hat, where R hat is our unit vector that's always radially outward. Okay, now we have our electric field inside the sphere as well as outside the sphere. Now the next order of business is to find the electric potential inside and outside. Now I want to start with part B and find the electric potential outside the sphere where R is larger than R0. This makes much more sense and a lot more easier to do so, and you're going to see why once we solve this problem. So imagine that I am interested in the electric potential at this point P here, and let's say the distance from the center of the sphere to point P is R. Now the expression we want to make use of reads as VB minus VA is equal to negative E dot dl from A to B. Now if you look at this expression, what you're going to realize is this expression does not give us the electric potential at a specific point, but rather a potential difference between 2 points. So how can I make use of this expression to calculate the electric potential at a specific point? And the answer to that question is, we will make one of these the electric potential at point P, and the other one a point where we know the electric potential. And for any charge distribution, we know that the electric potential will be 0 at an infinitely far away point. So we are going to make this V infinity. What I'm trying to say here is we will calculate Vp minus V infinity is equal to minus infinitely far away to point P E dot dl. And I know that this is 0. So we will find Vp by simply calculating this integral from infinitely far away to point P. Earlier on, we said that the potential difference does not really depend on the path taken, but rather it depends on only the final and initial points. So to make it easier, I will choose the easiest path possible, which is going to be basically a straight line from infinity to point P along the radial direction. And along the way on my journey, the electric field in this expression will always be the electric field outside of the conductor, because I never go inside the conductor during our journey. And we have to define also the dl vector here. So we need to divide the path into infinite small dl vectors. So the dl vector that I'm going to define, let's say at this point, dl vector will point radially outward direction. I'm going to define it as r hat dr. And within this dl vector, my electric field also points along the radially outward direction. So let's say this is our electric field, and we already know the answer to this question, which was 1 over 4 pi epsilon 0 q over r squared r hat. Or if you want, you can write it as k q over r squared r hat. So this is our electric field vector. Now some of you might say that, okay, but I thought we were coming from infinity to point P. Shouldn't we take dl vector in the opposite direction? But as a rule of thumb, this is what I would recommend to you guys. Always choose your dl vector in the direction where your variable is increasing, and take care of the direction with the limits of the integral as seen here. Otherwise, it is quite easy to make a sign mistake in your calculations. Alright, now we are ready. We can calculate E dot dl, plug in the limits, and find the electric potential at point P. So here, E dot dl will be equal to k q over r squared r hat dot r hat. Since r hats are unit vectors, the scalar product of r hat with itself will be basically 1, and then you're going to have dr here. So Vp will be equal to minus E dot dl from infinity to point P, which is going to be minus k q over r squared dr. Here I'm going to be much more specific with my limits, because now the integral is with respect to r, which is the distance from the center of the sphere to the point of interest. So when I'm at infinity, distance to the center of the sphere will be infinity, and when I'm at point P, the distance to the center of the sphere will be r. And if we continue with this integral, we are going to have, let's take the constants out. K is constant, q is constant, so we're going to have k q, and in the integral we have basically just r squared left, dr over r squared from infinity to r, and the integral of r squared is minus 1 over r, minus 1 over r, with the limits from infinity to r. And if we plug in the limits here, when you plug in the limit infinity here, 1 over infinity will give you simply 0, and when you plug in r, you are going to end up with just 1 over r. Two minus signs here will make our result positive. So apparently the electric potential at point P is nothing but k q over r. Or if you want, you can write this as 1 over 4 pi epsilon 0 q over r. So we find our electric potential. Outside the conductor as a function of r, when r is larger than r0. One thing to note here is the fact that the electric field of a conducting sphere is just like the electric field of a point charge. So it's only natural to expect the electric potential of this spherical conductor to be also just like point charge, which indeed it is. Alright, now that we are done with the electric potential outside, let's go ahead and calculate the electric potential inside this conducting sphere, where R is less than R0. Again, what we're going to do is we're going to make use of the same approach here. So we're going to choose a point within the sphere, which I'm going to call that point P. Minus V infinity is equal to minus from infinity to point P E dot dl. And just like what I did before, to make it simpler, I would like to move on a straight line. So I'm going to come from infinity to point P. Okay, now I guess we can put it in here. So point P is here within the sphere, and I'm going to define R as the distance from the center of the sphere to the point P here. Outside, the electric field and the dl vectors are still going to be the same. Inside, however, the dl vector is still the same, r hat dr, but the electric field inside is 0. So you see, while we are coming from infinity to point P, we actually go through two distinct regions where the electric field in one of them is kq over r squared, and in the other it is 0. So maybe what we should do is we should express this integral as sum of two integrals for two different regions. So I'm going to come from infinity to the surface of the sphere, E dot dl. So I came from infinity to here, and then from here I will go to point P, which is going to be from the surface to point P E dot dl. Here, however, this is the electric field inside, because from the surface to point P I am within the sphere, and here this is the electric field outside, because I am outside the sphere as I'm going from infinity to the surface of the sphere. And as you can guess, the scalar product of the dl and the electric field inside will always be 0, because the electric field inside is 0. So this term will simply go to 0. So all we have to do is to calculate this integral to find the electric potential at point P, because we know that this guy is also 0. So let's go ahead and do that. So Vp is equal to from infinity to the surface E dot dl, and the scalar product of the electric field and the dl vector is going to be kq over r squared dr. R dot r is 1, because these are unit vectors, just like what we said before. So we are going to have kq over r squared dr. Again, we can be a bit more specific now when it comes to the limits of our integrals. When I'm infinitely far away, the distance from the center of the sphere to the point is infinity, and when I'm on the surface, the distance to the center of our sphere will be r0. And if we solve this integral, let's first take the constants out, k, q. Inside we have dr over r squared left, so we have dr over r squared from infinity to r0, which is going to give us minus kq minus 1 over r, again from infinity to r0. When you plug in infinity here, you're going to get 0 again, and if you plug in r0, you're going to get 1 over r0, which means the electric potential inside will be equal to k q over r0, which, by the way, has no dependence on r, our variable. So inside the conductor, apparently the electric potential is constant. So it is not 0. Okay, now that we know the electric potential inside and outside of this conducting sphere, as a last exercise, let's plot the electric potential as a function of r, the distance from the center of this sphere. And let's do that on a new board. Just to remind you, this is our electric potential inside, which is constant, kq over r0, and this is the electric potential outside, which goes down as 1 over r. If we plot our electric potential here as a function of r, now within the conductor, apparently the electric potential is kq over r0 and it is constant. It will be constant all the way up to r0. And from the surface, it will go down as 1 over r. This concludes our example with the conducting sphere. Now what I would like you guys to do is, I would like you to repeat this approach for an insulating sphere with the same amount of charge, with the same radius r0, and find the electric potential again inside the sphere and outside the sphere. Now the only difference between this and the conducting sphere would be what happens within the insulator. So you try to solve this, and hopefully next week or the week after that, I will post the solution to this problem at Learn. Okay, now let's move on to our last example. Our last example deals with a parallel plate setup, and we know the electric field between two charged plates with charge density sigma and minus sigma to be from positively charged plate to the negatively charged plate with a magnitude of sigma over epsilon 0. But the question was actually generous enough to let us know the actual value of the electric field. Apparently that is 1000 newtons per coulomb, and the separation between the plates is given to us as 5 centimeters. It's asking us to figure out the potential difference between these two plates, and also it's asking us which plate is at a higher potential. Now, if you guys remember our discussion earlier, we said if you move through an infinitely small displacement vector, the change in the electric potential you are going to see would be E dot dl. And from here we concluded that if you move in the same direction as the electric field, you will see a decrease in electric potential. Now between the two plates, the electric field always points from positively charged plate to the negatively charged plate, which means if you go from positively charged plate to the negatively charged plate, you will see a decrease in electric potential. So from here we can conclude actually that the positively charged plate is at a higher potential. Okay, now that we figured out which one is at a higher potential, now let's see if we can calculate the exact value of the potential difference between these two plates. And for that, let's move on to the next board. Now I chose a coordinate system as shown here. So this is x is equal to 0. This is the position of the positively charged plate, and x is equal to d is the position of the negatively charged plate. And the expression that we are going to make use of to calculate the potential difference is still the same. VB minus VA is equal to minus E dot dl, where you go from A to B. Now obviously what we are going to do is we are going to go from one plate to the other. And since I already discovered that the positively charged plate will be at a higher potential, I want my result to be positive, so I'm going to calculate V plus minus V minus. So this is the potential at the positively charged plate, and this is the electric potential at the negatively charged plate, and this is going to be a positive value, which is obviously going to be from negatively charged plate to the positively charged plate, E dot dl. Now all I have to do is express E as a vector, dl also needs to be expressed as a vector, and find the scalar product and solve for this integral. So I'm going to call this delta V is equal to, now our electric field is in the positive x direction, so we can write it as E times I hat, where E is constant, by the way. It's given to us as 1000 Newton per coulomb, remember. And the dl vector usually is expressed in Cartesian coordinates as I dx, j dy, and k dz. But remember what we said about moving perpendicular to the electric field. So it won't make any difference. So what I'm going to do is I'm just going to express my dl vector as I dx, because any other motion that's perpendicular to the electric field will not create any potential difference, as we said before. So now that we have our dl vectors and the electric field vector, all we have to do is plug these guys in here and find the electric potential difference, which is going to be the scalar product of these two will be equal to E times I dot I times dx, which is E times dx. And the limits are going to be the negatively charged plate's position to the positively charged plate's position. Now the negatively charged plate is at x is equal to d, so I'm going to put this guy here, and the positively charged plate is at x is equal to 0. Now remember, E is constant, so I can take it out, so I take E out, and all I have left inside is dx from d to 0, and the integral of dx is nothing but x, so negative ex from d to 0. When you plug in 0 here, you're going to get 0, and you're going to subtract from that d, so it is going to be equal to minus e times 0 minus d. The minus minus will give you a plus, so apparently the delta v in this case is going to be equal to e times d. Now we know the values of the electric field and the separation between the two plates, so we can actually calculate a numeric value for the potential difference. So delta V is equal to, remember the electric field was 1000 Newton per Coulomb, and D is 0.050 meters. So if you calculate that, you're going to find delta V to be actually 50 volts. So this is our answer. Here, I should also point out that this answer does not really give us the exact potential that these individual plates are at. Rather, it's only giving us the difference between these two plates. What it means is, if this guy is at 0 volts, then this has to be at 50 volts. Or if this is at 25 volts, then this has to be at minus 25 volts. Or 0 volts minus 50 volts. Or 75 volts and 25 volts, for all of which delta V is 50 volts. So with this example, we conclude our first online video lecture. I will see you all later. Have a nice day.